Chapter 9, Section 9, Representations of Functions as Power Series, Part 2, Derivatives and Antiderivatives of Existing Power Series. Let's consider any power series of the form S of x. In this case, we're going to center our power series at an arbitrary value a, looking at the sum from k equaling 0 to infinity c sub k of x minus a to the k. We can obtain two new series from this series. The first series is d of x, which is the derivative of the original series. D of x would be the sum from k equaling 1 to infinity of k times c sub k x minus a to the k minus 1. A second series, a of x, can be found by taking the antiderivative of the original series. A of x would therefore be equal to some constant plus the sum from k equaling 0 to infinity of c sub k times x minus a now to the k plus 1 over k plus 1. So taking the antiderivative of the formula within the sum. This raises a couple of questions. First, do the derivative and antiderivative series have the same radius of convergence as the original series? Secondly, if the original series and the derivative series both converge on the same interval of convergence with radius r, is the derivative series truly the derivative of the original series in the ordinary calculus sense? And if the original series and the antiderivative series converge on the same interval of convergence with the same radius r, is the antiderivative series truly the antiderivative of the original series in the ordinary calculus sense? Let's consider a theorem to answer these three questions. If the power series that we've just considered from k equaling 0 to infinity has a radius of convergence r greater than 0, then we can define a function f as f of x equaling c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared, which is really the sum from 0 to infinity of c sub k x minus a to the k. We consider that that is differentiable and continuous on an interval a minus r to a plus r, and that we can obtain two additional series. So this theorem allows these additional series, the derivative series, k equaling 1 to infinity of k c sub k x minus a to the k minus 1, and the antiderivative, constant plus k equaling 0 to infinity c sub k times x minus a to the k plus 1 over k plus 1 to exist. In addition, the theorem tells us that the radii of convergence of the power series for both the derivative and antiderivative series are both r, just as the original series. Based on this, we can now answer those three questions. The derivative and antiderivative series do indeed have the same radius of convergence as s of x. That was the last statement in the theorem. Additionally, the original series and the derivative series converging on the same interval means that the derivative series is the derivative of the original series in the ordinary calculus sense. It is differentiable and continuous. Therefore, the derivative series must also be the derivative of the original series. Lastly, the original series and the antiderivative series converging on the interval negative r to r with that radius of convergence of r means that the antiderivative series is truly the antiderivative of the original series in the ordinary calculus sense. With this information, we can now consider new ways to create power series. Let's find the power series representation for 1 over 1 minus x squared. You'll note that this function is not a similar form to a geometric series. Therefore, the technique we used for the earlier examples in video number 1 don't necessarily apply. But the observant calculus student will note that g of x equaling 1 over 1 minus x quantity squared is really the derivative of 1 over 1 minus x. Oh. If we can find a power series for 1 over 1 minus x and take the derivative of that, we will therefore get the power series for little g of x. The power series for 1 over 1 minus x is 1 plus x squared plus x cubed, the standard geometric power series, which is given by k equaling 0 to infinity of x to the k. Taking the derivative of 1 over 1 minus x gives us 1 over 1 minus x squared. The derivative of 1 plus x squared plus x cubed is 1 plus 2x plus 3x squared plus 4x cubed. And therefore, taking the derivative of x to the k is k times x to the k minus 1. But now we're going from 1 to infinity because we've lost the constant term from the original. Now we have a power series for g prime. That means we also have the power series for little g. And we can say that little g is the sum from 1 to infinity of k times x to the k minus 1, which is 1 plus 2x plus 3x squared plus 4x cubed, dot, dot, dot. We'll note that this power series has the same radius of convergence as the original series 1 over 1 minus x. Since 1 over 1 minus x is the standard geometric power series and has an interval convergence of -1 to 1, the radius of convergence there is 1, and therefore the radius of convergence for 1 over 1 minus x quantity squared is also 1. Let's consider a second example. Let's find the power series representation for ln of x. Well, this isn't a rational function, but we know the derivative of ln of x is 1 over x. So manipulating 1 over x, we can say the following. That 1 over x is 1 over 1 minus 1 plus x, or 1 minus the quantity 1 minus x. That's really 1 plus 1 minus x plus 1 minus x squared, or the sum from k equaling 0 to infinity of 1 minus x to the k. But we don't like it being 1 minus x, so let's manipulate it into the sum from 0 to infinity of -1 to the k x minus 1 to the k. Now we can take an antiderivative. Integrating on both sides, we set up our integral, and we obtain that ln of x is equal to a constant plus k equaling 0 to infinity of -1 to the k x minus 1 to the k plus 1 over k plus 1. Since ln of 1 is 0, our constant will turn out to be 0, and therefore the power series expansion for y equals ln of x is simply k equaling 0 to infinity, -1 to the k, x minus 1 to the k plus 1 over k plus 1. This concludes our video.